Hi there, thanks for watching this video series of reinforcement learning with TensorFlow Agents. My name is Wei, and I'm a developer advocate at Google. One of the most exciting breakthroughs in machine learning in recent years is AlphaGo. AlphaGo and its successors heavily use reinforcement learning to train Go, chess, and shogi agents to achieve superhuman-level gameplays. So in this video series, we'll be exploring the exciting field of reinforcement learning and show how you can leverage TensorFlow Agents, a powerful TensorFlow library, to build your own reinforcement learning agents. Since TF Agents is based on TensorFlow, we're going to assume you already have a solid machine learning background and are familiar with TensorFlow 2. For example, you should already know how to build and train a neural network with Keras, and if you are ready, let's get started. Let's first take a look at an example. When you take a walk on the street, it feels quite natural. That's because you have been practicing walking since you are a toddler. But if you want to train a robot to walk from scratch, that's quite challenging. Here you see we're trying to teach a small four-legged robot to walk. It just keeps failing at the beginning. But after 1800 episodes of reinforcement learning training, the robot is able to figure out how to walk effectively without falling over every 2 seconds. This is the power of reinforcement learning. Reinforcement learning is a general framework where the agents learn to perform actions in an environment in order to maximize the reward. In reinforcement learning, there are several important components. The agent is what we're trying to learn. The agent takes an observation of the environment and then generates an action. We call this the rule of generating the action policy. We then feed the action back to the environment. And lastly, the environment provides a reward signal to let the agent know how it's doing. If you are already familiar with reinforcement learning, you probably have noticed that I'm skipping the concept of state here for simplicity. In this video series, we're going to assume full observability and use observation and state interchangeably. Reinforcement learning is one of the three machine learning paradigms, along with supervised learning and unsupervised learning. You are already familiar with supervised learning, in which case we need ground truth labels to do the training. But in our previous robot walking example, we do not have clearly defined labels for successful walking, since the robot can walk in many different ways. In contrast to the supervised learning scenario, in reinforcement learning, we train agents to discover the best decisions to take in order to reach the goal. Since the ground truth labels are not available, our agents have to learn by trial and error. For example, they wander around the problem space and figure out which paths lead to the goal. More specifically, reinforcement learning needs to interact with the environment to collect the reward data to enable training. These data are not static, and they are not even necessarily the right answers since they are specific to the actions taken. There are often multiple surrogate losses, multiple optimizers, and multiple copies of the model variables involved, which makes it very challenging to train. And lastly, unlike supervised learning, a simple model.fit generally is not sufficient. Generally speaking, there are two kinds of RL algorithms, model-free and model-based. Here, model means a state transition function that predicts the next state and the reward during the transition. It is not the neural network architecture in our typical deep learning scenario. In model-based RL, we try to learn a transition function to optimize the agent's behaviors. In contrast, in model-free RL, we do not learn this transition function. We'll be focusing on the model-free RL in this video series. In model-free RL, there are value-based methods and policy-based methods. In value-based reinforcement learning, we learn a function that predicts the value of the action based on the agent's state, and then we choose the best action to optimize the agent. In policy-based RL, we directly train the agent to pick the best action based on the agent's state. DQN is a classical value-based method. We'll be discussing it in our next video. Reinforce, also called policy gradient, is a policy-based method. We'll be discussing reinforce in the third episode of this video series. And lastly, We can also combine value-based methods and policy-based methods. These are called actor critique methods, and we'll be showing you a SAC soft actor critique method in the fourth episode. Now that you have a basic understanding of reinforcement learning, let's take a look at some of the cool applications in the real world. We briefly mentioned AlphaGo at the beginning of this video. It is truly an inspiring breakthrough in the field of reinforcement learning and machine learning in general. Gaming has always been the testbed of reinforcement learning. The Falcon project Google open-sourced recently helps game developers quickly train game-playing agents to test their games. Falcon uses TF agents under the hood. We'll learn about TF agents starting from next episode. In addition, Google Stadia team uses reinforcement learning to test their game characters and adjust the game balance during their Chimera game development. Other than applications in games, Google research team is using reinforcement learning to design chips with faster and better results. You can check out this video from our ML Community Day to learn more about this cool application. Reinforcement learning also helps Google save 40% in data center cooling bill and significantly reduce energy usage. Lastly, reinforcement learning has been widely used for robotics research at Google. Here's a cool demo of training a robot arm to open a door. A few minutes ago, we talked about the key components of reinforcement learning. The one component I want to highlight in this episode is environment. Since we need to have an environment that the agent can continuously interact with to collect the data, this means we need a tool to easily create these environments. One of the most widely used training environment toolkits for reinforcement learning is OpenAI Gym. Gym provides a set of standard RL test environments, such as Atari games and classical control environments. Here's one of the most widely used gym environments, cart pole. The task is to train an agent to move the cart left or right so that the pole on the cart is balanced and don't fall down. Random agents will quickly make the pole fall down, and while a trained agent will keep the pole perfectly balanced as you see on the right. Instead of using the built-in gym environment, you could also define a custom environment for your own needs. You only need to define 5 functions: init, step, reset, render, and close. The most important one is the step function here. Step defines how your environment interacts with your agent. It takes in an action, makes some internal state changes, and then returns a new observation and a reward signal so that you can use this information to train your agent. Feel free to check out how the cart pole environment is implemented within OpenAI Gym. So to summarize, today we gave you a high-level overview of reinforcement learning by showing you what reinforcement learning is, how it is different from supervised learning, and what kind of RL applications there are. If you want to learn more about reinforcement learning theory, make sure to check out the course taught by DeepMind and University of College London. In our next episode, we'll introduce you to TF Agents, a powerful reinforcement learning library, and show how you could use a value-based RL method, DQN, to train a cart pole agent. See you next time.